Hello students, myself Dr. Mahantesh K. Welcome you all to this video lecture series on electromagnetic waves of Module 4, Class 2. In our previous video, we have introduced Lorentz equation and what is the force exerted on a moving charged particle in an electric field and what is the force exerted due to a moving charged particle in a magnetic field is called as magnetic force. And we obtain the relationship between electric force and magnetic force using Lorentz force equation in the previous video. In this video, we are going to discuss more about differential current elements and the force equation which is caused due to differential current element. The first you need to understand what is the force between the current element. When a current carrying conductor is placed in an external magnetic field, the magnetic force Fm will act on the conductor. However, the conductor carrying current also generates its own magnetic field. Hence, if there are two current carrying conductors, then each conductor will exert a magnetic force on each other. Hence, if there are two current carrying conductor, there will be a force, a magnetic force on the other. Now let us consider the two current carrying conductors I1 dl1 and I2 dl2. It's a differential current elements as shown in this figure. I1 dl1 is the differential current element and I2 dl2 is the differential current element of the current carrying conductor 2. Assume the directions of I1 and I2 are the same direction. The differential amount of differential force exerted on element I1 dl1 due to the field dB2 which is generated by the other current element I2 dl2. Usually it is an attractive force which is given by ddf1 is equal to idl1 cross db2. This equation was obtained in our previous video. So according to the Biot-Savart's law, the magnetic field produced by current element I2 dl2 in free space is given by the Biot-Savart's law dB2 is equal to mu naught dH2 which is equal to mu naught I2 dl2 cross AR21. What is this AR21? This is the unit vector from conductor 2 to conductor 1 divided by 4 pi R21 square. Therefore, dB2 is equal to IDL2 cross AR21. Substituting equation 1 in equation 2, we will obtain what is equation 2? This is equation 2. In equation 1, so for dB2, if we substitute this value, d df1 is equal to mu naught I1 dl1 cross I2 dl2 cross AR21 divided by 4 pi R21 square. What is R21? R21 is nothing but the distance between the conductor to the magnetic field at the point 1, that is the current carrying conductor I1 dl1. Integrating equation 3 twice, we will get the total force exerted on current element 1 due to the magnetic flux density B2 produced by the current element 2. It's given by F1 is equal to mu naught I1 I2 by 4 pi line integral of L1 to line integral of L2 of dl1 cross dl2 cross AR21 divided by R21 square. R21 is given by R1 minus R2. Similarly, the force exerted on a current element 2 due to the magnetic flux density B1 produced by current element 1 is given by F2 is equal to mu naught I2 by I1 by 4 pi line integral L1 to line integral L2 divided by dl2 cross dl1 into AR12 divided by R12 square. We can write the relationship between F2 and F1 as F2 is equal to minus F1 since A of R12 is equal to minus A R21. Equation 6 also shows that two elements carrying current in same direction attract each other with equal forces. If the currents are in the opposite direction, the current element will repel each other with equal forces if the currents are in the same direction. Now let us try to solve some simple problems using the differential current elements as well as the Lorentz equation. A charged particle moves with a uniform velocity f in the direction ax meters per second in a region where E is equal to 25 ay and B is equal to B naught az. Determine B naught such that the velocity of the particle remains constant. So when the charged particle moves with a constant velocity, the acceleration remains 0. Therefore, F is equal to ma, which is equal to q of E plus V cross P is equal to 0. Substituting all the values here, we know that ax cross az gives minus ay. Therefore, q is equal to 25 ay minus 5 b naught ay. Therefore, 25 ay is equal to 5 b naught ay. Therefore, b naught is equal to 5 Weber per meter square. Second example. Find the force on charged particle of mass 1.7 into 10 power minus 27 kilograms and charge quantity 1.602 into 10 power minus 19 coulomb. If it enters a field of magnetic flux density B 10 milliweber per meter square with an initial velocity of 90 kilometers per second. F is given by Q V into P. I have assumed B and V are perpendicular to each other. So QVB sine theta, theta is equal to 90, sine 90 is equal to 1. Therefore, F is equal to the product of QV and B. It's given by 14.42 into 10 power minus 17 newtons. You take up another example. A point charge of 4 coulombs moves with a velocity of 5 ax plus 6 ay minus 7 az meters per second. Find the force exerted if the magnetic flux density is given by 5 ax plus 7 ay plus 9 az. So now we know that magnetic force, is equal to Q V cross B. V cross B can be solved using a determinant form as shown in the matrix Ax, Ay, Az, identifying the components of V in terms of Ax, Ay, Az as well as B in terms of Ax, Ay, Az, substitute and find the determinant. So we get V cross B as 103Ax minus 80Ay plus 5Az. Substituting this into the magnetic force equation, Fm is equal to 412Ax minus 320Ay plus 20 Az newtons. Hence, the magnitude of the magnetic force is given by 522.05 newtons. Similarly, another problem where the velocity is given by 5 into 10 power 6 in the direction specified by the unit vector. So here the velocity, the vector velocity is the product of a magnitude velocity and the unit vector. Therefore, the force equation is equal to Q into V cross B. Again, it can be solved using determinant form, and the magnitude of the force is given, calculated, and the solution is 1.389 millinewtons. Another example, a wire of length 1 meters, that is L is equal to 1, carries a current 10 amps, I is equal to 10, makes an angle of theta degree, 30 degree, with uniform magnetic field of flux density B 1.5 Weber per meter square. So we can calculate the force on the wire given by BIL sine theta, which is equal to 7.5 newtons. So very simple problem and a simple substitution to the equation of force. This is a Lorentz equation in magnetic field. Similarly, a conductor carrying current 6 meter long lies along Z direction. Current 2 amps in AZ direction. Find the force experienced by the conductor if B is equal to 0.08 AX direction. We know that AZ cross AX is equal to AY. Therefore, F is equal to IL cross B can be obtained as 0.96 AY newtons. So we have another example with the same conductor carrying current of length 2.5 and Z equal to 0 and X equal to 4 meter, carries a current of 12 amps in A minus AY direction. Calculate the uniform flux density. Here I've asked you to calculate the force. Now I am asking you to calculate what B in the region if the force of the conductor are given F here, I and L is given. So I'm asking you to calculate what? A B in the region. So this seventh problem, you take it as an assignment and submit it as soon as you watch this video lecture. Thank you for watching this video. Hope you have enjoyed this video on differential current elements and of course some simple problems on differential current elements. Thank you.